Okay, welcome to the third class meeting of EECE341, Introduction to Communication Systems. Last week, we reviewed the history of communications and history of electrical communications, where I talked about this stuff. So especially for the electrical communications, we know the history from the physics. Volta invented the device so-called battery, with which many people started to experiment about electrical circuits. They had no idea how to exactly mathematically model the electrical circuit, but eventually Maxwell's Heaviside equation came up, and people started to simplify the Maxwell's equations to have very good approximate equations like Kirchhoff's voltage law, current law, something like that, Ohm's law, and other things. And due to the evolution of the electrical circuits, devices, and systems, we could perform many other operations which before we could not operate. So our human beings started to make it possible to use materials to compute something. Mathematical computation, logical computation, algorithmic procedure, that kind of good things started to be implemented using materials without life. Can you believe that? We can compute 1 + 1, and probably monkeys cannot do that, but our cell phone can do that. Isn't it amazing? So with the help of evolution of electrical engineering, we could do more and more operations that is good for our communications. So eventually, after this evolution, we currently have the wired network, so-called the internet, and wireless network, so-called mobile cellular communication network. And we are enjoying transmitting information, storing information. Everything's have been possible, and this evolution is going on. That is the lesson you need to know. So due to the help of very fast computation and logical operations, now there are more and more good things we can do for better communication. Someday, as one of the industry leader like Elon Musk says, we may have some chips inside our brain and may communicate with each other. Someday, that may be possible. I don't know, but if we just project the current rate of evolution of our electrical engineering, why not? It may be possible. Okay. Anyway, so this is the lessons. By the way, let me do some administration stuff as usual. Handouts for chapter 2 is downloadable, and you may say that, wait a minute, some materials in the handout for chapter 1 is not yet covered, and I found that that would be covered at the end of the semester because most of the material is about information theory. So let me just directly move to the chapter 2 material. So if you haven't yet downloaded, please do so now. And about homework 3, in order to help you to review the signal gen systems material and better prepared for the quiz, I have set the due this Friday. So there will be 2 more homeworks before your quiz. Got it? So one is on this Friday, and the other is on the quiz day. So I will divide the signal gen systems material which are needed in this course into 2 homeworks. Got it? So please review very diligently. Otherwise, you may find yourself not well prepared for this entire course because we are going to heavily rely on the Fourier analysis, which is covered in our prerequisite course, Signals and Systems. And as I announced, quiz 1 will be taken immediately after the Chuseok break. So from 9:30 to 10 a.m., we are going to take the quiz. And you must be able to access PLMS because the problems will be available from PLMS and your solutions or answers must be uploaded or punched in on the PLMS. So you must have some network enabled device to take quiz. By the way, some of the students asked whether it is open book. Yes, it is open everything quiz. So you can bring anything you want. You can access internet. However, as you know, from my previous courses, communication among you or with a human being is not allowed. You can communicate with a large language model if you want. But usually what I do is that some questions I test with very famous LLMs. And if they answer wrong answers or which is not expected me, then usually I put it on the quiz. So if you just rely on an LLM, then you may have some strange answer, and I will just I will give you a 0 score for that. So LLM may be useful, however, don't believe them, okay? I test, and whenever they answer incorrectly, then I'm encouraged to put that question on the quiz, got it? So it is an open everything quiz. You can bring your Signals and Systems textbook if you want, but as I told you, we have only 13 minutes, so you may not have enough time to flip over your old textbooks. You need to memorize some important equations. You need to memorize how to solve some important problems, how to prove some important equations, something like that. Okay, let me go back to our this preview. So today, we are going to cover the chapter 2 handout. So it's all on signals and systems. Especially, I will cover the signals part. I will talk about Fourier series, Fourier transform, and what's the meaning of that. Okay, so here goes the signals and systems. Just a second. So last time I made a mistake in the spelling of Lorentz name. So there must be T, right? So as you've seen here, where it is, yeah, there must be T here. Lorentzian force. So as last time I emphasized, all electrical engineering except quantum mechanical results, everything relies on these 5 equations. Maxwell's Heaviside 4 equations and Lorentz force equation. As I repeatedly told you, without force equation, we can't even think about linear motor or something like that. We have to compute the force in order to move something. Anyway, one of the reasons why I put this book, this is a kind of popular science history book written by some PhD in mechanical engineering. I strongly recommend for you to read it. Some of you may have found Carl Sagan's Cosmos one of the life-changing book you've ever read. Personally, that book was one of my favorite for around 40 years. However, I changed my mind. This is the best about history of science. This is written by Korean. Okay. Anyway, he is actually provides lectures to the mechanical engineering students, undergraduate students on this semester. His special topics lecture for undergraduates are offered every Thursday, Thursday, Wednesday, I'm not sure. Anyway, so ask your mechanical engineering friend whether Dr. Peggy Min is lecturing at what time slot this semester. Anyway, where he talks about, because his major was about turbulence in liquid or gaseous molecules. So he talks about everything about, how to say that, fluid mechanics or something like that. And as an electrical engineer, when I was taking an electromagnetics course, not only in my sophomore course, but also in physics course, I wondered why we have those strange differentiations like curl divergence to describe behavior of electric field and magnetic field. And interestingly, at that time, at the period of Maxwell and Heaviside, mechanical engineers have developed a lot of good mathematical tools already to solve their problems related to turbulences, liquid flow, and those things. And interesting thing is that since those discovery was so successful, and also due to some myth about the propagation of light wave, people tried to use those fluid-based approach to mathematically formulate the equations for electromagnetism. So probably some of you have seen Maxwell's original thesis, where he talks about something circulates. Actually, he divided the entire space with very small cubes where something was circulating. And that something was actually ether or ether. People believe that there existed some medium through which light wave or electromagnetic wave propagates. That was called ether or ether, right? And the theory was based on wrong conception, actually. However, the result was exactly correct. And some of you may say that, wait a minute, as Newtonian mechanics is a simple approximation of Einstein's general relativity and special relativity, probably Maxwell's equations is also a low-speed approximation of some new idea or something like general and special relativity for electromagnetics. Actually, what Einstein discovered, and unlike what you have read in your undergraduate physics book, actually Einstein's special theory of relativity was about relativistic effect on electromagnetic wave. So he already considered why this is true, even though there is relativity, something like that. So if you read some books, there is a very interesting statement. Even after the invention of special and general relativity, no modification is made on Maxwell's equations. Why? Because Maxwell's equations somehow already reflects the relativistic effect. And you may wonder, really? Is magnetic field, electric field, those things already incorporates relativity? And actually, that is yes. And in Einstein's thesis, he showed what? He showed magnetic field is an effect of relativity on electric field. So that effect is shown us as a magnetic field. So no modification is made. And interestingly, due to the relativistic effect, to us living in non-relativistic world, there seems to exist some magnetic field. Got it? Anyway, so these equations are exact even after the discovery of relativity. The problem is that even though there are only 5 equations, depending on the environment of our system, electrical system, we have to solve partial differential equations to exactly know what would happen in our, for example, circuits, so-called circuits that consist of wires and some ohmic materials or something like that. So scientists and engineers have simplified Maxwell's equations for circuits. That's what you learned in circuits course. Of course, there is some part where quantum mechanics or quantum physics needs to be discovered, and I will talk about that. Anyway, so remember this. Our magnetic field is actually the relativistic effect of electric field. And we just call it, because it behaves strangely, we call it a magnetic field. And circuit theory is an approximation of Maxwell's equations. By the way, in order to analyze radio propagation characteristic, 전파 특성, what do we do usually? We usually adopt ray-based model. And some of you already know from geometric optics, like there is an incident angle, reflection angle, something like that. Those are all approximations for light waves, right? And there is a very vague boundaries where you really need to use Maxwell's equations. But on some vague reason, you just use ray-based approximation and everything works well. For example, if we look at, for example, a mirror, then you can just assume that there exists some ray directly connecting the image there and me, and there is a line of sight or reflected path, something like that. So this path-based, ray-based approximation also works very well. And our mobile communications people actually almost never use Maxwell's equations. So when I came to postdoc, some mathematics department professors invited me to provide them a talk. And as a wireless communications engineer, I talked about our field. And at the end of the talk, one of the professors who is going to retire this end of this semester asked me, "Hey, Professor Cho, where is Maxwell's equations? You said you are a radio communications engineer, and you never talked about Maxwell's equations." And my answer was that I don't exactly remember those equations. And still, I do not remember. Probably, if you ask me, "Hey, Professor Cho, write 4 equations," probably I will stumble a lot. Is it a curl or something? The reason is that we make approximations from Maxwell's equations. So if you really hated electromagnetics, it's okay to become a radio communications engineer or radar engineer. See me. I have been not that unsuccessful in this area, and I have no idea about Maxwell's equations now. Of course, when I was at your age, I was very good at in those courses. But so remember that there are many levels of approximations for Maxwell's equations, and depending on your future research area, you will use different approximations, different level of approximation. But remember that every simplification and approximation has its limitation because it's an approximation. So sometimes your simple model, like ray-based model for most of the communications problems, may fail due to that approximation. In that case, we have to go back to the Maxwell's equation. And actually, that is happening in my field. For example, usually we assume that transmitter and receiver is separated far apart enough, which means that it's separated more than several wavelengths. However, your cell phone, probably you use your cell phone to open the lock of LG research building. In that case, your transmitter and the door lock, the receiver, has distance smaller than the wavelengths. In that case, your ray-based model for radio propagation characteristic may fail because that is below the limitation of your ray-based model. So people claimed that, hey, let's have a better approximation, but not Maxwell's equation. So let's use not parallel wave front end, which is the base of the ray-based model. Now let's use spherical front end model. That's reasonable, right? And then they could successfully analyze what was wrong and what could be done and what is good for new model, something like that. Now, let's talk about signal gen systems, because that is the topic of this week. So this is a simple block diagram for single source to single sink or destination communication. And sometimes we call this type of communication as a point-to-point communication, because there is a single transmitter and single receiver. Sometimes single input, single output communication system. But anyway, let's consider a very simple model. Here, I especially considered radio communication, where we use radio wave of our electromagnetic entire spectrum. It usually have the device, passive device called an antenna, transmit antenna and receive antenna. What does that do? What is the role or what is the function of antenna? Antenna, simply put, converts electrical signals generated by our circuit or electrical system to a radio wave. And at the receiver, it converts radio wave to electrical signals that can be handled by our circuits in the receiver. Got it? So it's similar like a loudspeaker and a microphone in Bell's invention of the telephone, right? And microphone and speaker converted acoustic signal to electrical signal or vice versa. Similarly, antennas convert radio wave to electrical signal, vice versa. Of course, at the top, if we view everything, it's all about what? The problem related to solve some Maxwell's equations with boundary conditions. However, as I told you, we electrical engineers divide some areas, right? You can solve the entire thing using Maxwell's equation, but that is too much burden, and that is unnecessary in many cases. So we view that between these two antennas, we have to think about propagation of radio wave. However, just at the input of our antenna and just at the output of our receiver antenna, we could just assume that there is a current, electrical current at that point where we can measure the value as a function of time. So what is important is in circuits is the notion of current. So electrical current. And you may say that, okay, current is a time function. Done. However, that is completely wrong. Why? Because as I told you, due to the quantum physics, we now know that no electron with temperature non-zero Kelvin has uncertainty in its position and its velocity, right? We know that. Then how can we say that, okay, here is a wire. Let me count the number of electrons that passes from your left to right as a function of time. And we integrate those charges, and then we differentiate to get a current, right? So what you do is that your capital Q is integration of the number of electrons moves towards this direction, actually the opposite, and then times the charge, amount of charge in each electron, right? And then you have a function Q of T that accumulates all of the entire charges from time 0 to, for example, at some time t. And then you differentiate that Q of t as with respect to t. That is your current in the circuit. However, we now know that electrical charges are quantized. Then how can we differentiate that Q of t? Because Q of t function as if as like our discrete time random variables CDF, it is piecewise constant, right? How can you differentiate? That is the first thing. You have direct delta functions, right? But we mostly consider smooth curve for our current. That is the first thing. So what I say is that, precisely speaking, your concept of current as a function of time t, smooth function, never happens. Second thing is what is based on the quantum physics. You even do not know whether electron really passed that point where you observe capital Q of t, right? You have to use time varying probability density of that electron's position. Then how can the summation of those probability densities, time varying densities, can be simply modeled as mathematically modeled as a continuous time function that is even differential. So now you know that everything you simply assumed true in your circuits course was mere approximation of reality. However, that approximation has a very good range in which almost no error is made, even with that poor approximation. Got it? So anyway, in our signal chain systems, we ignore the fact that electrons, the electrical charges are quantized. So we assume differentiable functions for our signals. Sometimes not differentiable, and also we just forget about quantum physics. Okay. However, remember that if you join some research lab in your graduate study where they deal with very small current, because these days low power device is very important, right? What does that mean? Very small current. Now you may have to count the number of electrons. In that case, that smooth differentiable time function, the current, the notion of electrical current may fail. Got it? So remember this. Depending on your research field, this such and such model you learned in your undergraduate course may be a very good approximation or very poor approximation. So never forget that. This may be the best, one of the most important message for me to convey you today. Our mathematical models, all you learned in circuits theory and signal chain systems and other courses are approximations. Got it? Anyway, so here goes the figure. So here at this point, we can model the current or voltage applied to our antenna is what? Well modeled as, for example, a continuous time function, x of t. Got it? And also, we can make a good approximation that at the output of our receive antenna, the electrical current or voltage can be well approximated by a continuous time function. Now, given that model, we talk about the design of this transmitter and the design of this receiver. And what we do is like this as a communication engineer. Given the property of this propagation channel between transmit antenna and receive antenna, where radio wave propagates, depending on the characteristic of our propagation channel, we design our transmitter and our receiver pair we design pair of transmitter and receiver to best utilize this channel characteristic. Got it? For example, now suppose you are a NASA engineer in 1950s. You want to communicate in your future project, so-called Apollo mission. You want to communicate with your astronaut on the surface of the moon from your Cape Canaveral. Then what is the channel? The channel is the vacuum between the Earth and the moon. Now, you want to design the communication system that will be put on the Apollo command module and on your Earth station. Can you use acoustic signal? Of course not, because there is a vacuum. Can you use light wave? Well, due to the atmospheric turbulence, rain, snow, and dusts, of course, impossible. The only possible way is to use radio wave, especially at some specific range of radio wave, because our ionized sphere may reflect, actually that deflects, but it looks like it reflects our radio wave signal. So as you learned in the introduction to communications and network, ITU, the UN organization about the radio regulation, they usually assign some specific band for those spaced communications. And these frequencies can easily pass through our ionized sphere. Got it? Anyway, so here, what we do is that we want to build something that consists of metallic wires and some silicon-based something and some chemical-based something. And we want to build something that can generate this signal applied to the so-called transmit antenna. And here, what we want to do is that we want to design something that can handle this electrical current and extract the information that is transmitted from the transmitter. Got it? So you have to design something, the equipment's called transmitter and receiver that best utilize this channel characteristic. You have to select what kind of signal you use. For example, sometimes infrared is a very good choice because it can be easily blocked by simple walls. For example, this remote controller for our camera, usually they have LED, but if I push that button, that I can't see any light because usually this LED generates infrared, which is not visible, but very light wave like electromagnetic wave. And good thing is that since our classroom is usually blocked by the walls except the back door, even though I push the buttons in this classroom, the device, the TV set, or some cameras on the other classroom is not affected. And that's good, right? Because it cannot easily pass through the walls. However, sometimes we want our signal to pass through the walls, right? In that case, we have to select different, for example, things. I may use acoustic signals, and I may shout, and sometimes some part of the acoustic signal pass through the walls, or they anyway reach the people on the other side of the wall. However, maybe the choice must be made on the radio wave because some specific radio wave, especially low frequency radio wave, it can easily pass through the wall, or it can easily divert its path to reach the receiver. So anyway, what you do is that not only you just simply design, you also design what kind of radio frequency carrier you need to handle. So usually we have RF components, radio frequency components called oscillators, local oscillators that generates the so-called carrier, which is a sinusoidal signal. And we have RF mixers, RF amplifiers, RF filters, those things. So there are two types of communication engineering research lab, not only in our department, but also in every possible electrical engineering. One group of professors are like me. What we are doing is that we think about algorithms, mathematical procedures that is good for our better communication. So we heavily rely on mathematical modeling of the signals, and we handle convolution, filtering, those things every day. However, there is another communication major professors who are doing what? Research on radio frequency devices like amplifiers, oscillators, filters, antennas, and those stuff. So there are two types of communication engineers. Not only the communication engineers, but also the entire electrical engineering can be simply divided into two. And usually I say that there are two buildings in electrical engineering. In one building, the engineers who think about what kind of logical and mathematical operations are good for some purpose. And the other building, they think about how we can build electrical system to realize these algorithms or procedures, right? So you may even divide our electrical engineering courses depending on what is the nature of that course. This course is about this building on the right side, okay? On your I usually call I'm living in the right building, and there are left building, and of course computer engineer says that, oh no, there are one more building that is much bigger, and of course I may say that that is also a kind of extended building on the right side. Anyway, so in signal gen systems, probably you have already started to review the material you learned in signal gen systems. What I want to emphasize is this one. The time function you handled in signal gen systems is a mere approximation. Sometimes it's very good approximation, sometimes it's a very poor approximation. Whenever in your future research you have a problem in that model, then go back to Maxwell's equations and quantum physics. Got it? For example, consider you hired by NASA, and your first mission is that, hey, Mr. Kim, what you need to do is that you reconnect Voyager 1 to our communication network and say that, what is the received power? And say that, and your boss says that, okay, the distance is too far away, and actually we can count the number of photons that is sent by the Voyager 1. And that is really what is said. Of course, they have radio wave antenna. But anyway, the radio wave, if it is too far away, like current position of the Earth and the current position of Voyager 1, the deep space probe, that is too far away. And actually, what we do is that we count the number of photons, the number of, the radio wave tones. I don't know what is the exact word, but you say the number of photons received from the Voyager, something like that. In that case, your model, simple model, never works, right? Got it? Anyway, we will talk about other terms later. So let me go to the signal gen systems part. First, there are two kinds of signals that are handled in electrical engineering. One is a signal called a deterministic signal. And we can mathematically exactly model that. So every time t times 0, you have an assigned number. So this pair, for all t or for all T0 in which you have on the interval on which you are interested, then you have fully specified that function. Sometimes you may say that, okay, x of t equals a cosine omega 0 t for all t, or t, something like that, right? You've seen this form of signal a lot in circuits course, right? And in order to describe such a deterministic signal, how many time value pairs do we need? Usually uncountably infinite number of pairs, because you can change that time t or t0 for any real number. And what is the number of real numbers? Uncountably infinite, right? So your claim that you have a deterministic signal, what does that mean? You have uncountably infinite number of time value pairs. And another thing is that, what is this one? Again, we have approximation. There is no negative infinity according to our Big Bang theory. And if you believe that our current universe will terminate with Big Crush, then there is no plus infinity in our time. Then what does that mean? It's an approximation, engineering approximation. What does that mean? From our time of reference, t equals 0, long ago enough, and far, far future enough. And that far, far future and long ago may be just 2 microseconds. Sometimes it may be 200 years. But as you know that electrical systems has history less than 400 years, right? Before Volta invented the battery, no one had electrical signals with which play, right? So there is no negative infinity. But that is a good approximation in many electrical engineering system, because sometimes our time span of interest can regard 1 second, negative 1 second as negative infinity, 1 microsecond as positive infinity, depending on your interest. So that t greater than negative infinity and less than positive infinity is also an approximation. Got it? So this is also an approximation. There is another signal. So we know that we will observe, or we can make a very good approximation of that quantity as a time function. However, that signal has uncertainty. In that case, there are 2 approaches to handle signals with uncertainty. Usually two approaches. One is that we use our probability theory. In that case, the signal is usually called a random process. Of course, if the signal is not a time function, it is a scalar, then we call random variable. If it is a vector, we call it a random vector. If it is a time sequence, we may call it a discrete time random process. If it is a field, we may call it random field. If it is a graph, we may call it a random graph, something like that. There is another approach that is not well taught in most of the undergraduate courses, is so-called the chaos theory. So the chaotic theory approach is that they believe that the signal has no mathematical randomness at all. But due to some reason, like some small measurement difference in some nonlinear effect, we have uncertainty in the signal. In that case, there is no probabilistic randomness, no quantum mechanical randomness, but we have to model it as a deterministic signal with uncertainty, but not a random process. There is some approach, and there is some useful application. For example, you want to encrypt your message signal. And what you want is that for your eavesdropper means that your eavesdropper may there is no way other than view that received signal, intercepted signal as a random process because there are too much uncertainty. However, to your intended receiver, it may be just a deterministic signal. So you can decrypt the message, right? In that case, the same signal with some chaotic encryption code imposed must be modeled as a signal with uncertainty, and probably highly likely the eavesdroppers model it as a random process. However, your intended user may regard it as a deterministic signal, something like that. Got it? So depending on the situation, actually what we do is that we open our toolbox and search for a good tool that is best fit for their situation. So as an undergraduate student, what you have to do is, one of the things you have to do is that you have to fill up your toolbox with useful tools. That's why you have to take courses, you have to take diverse courses. I really worry about current trend in our undergraduate students. Some of my advisees came to me and say that I want to have so-called research participation. So because I rarely remember the grade of the students. So are you a senior? And student says that, no, I'm a sophomore. So a student just entered the university in 1 year ago and approached me that he or she wants to determine he or her future sub-major in electrical engineering. And usually those students have an attitude like this. I do not want to take all these courses. I want to take some branches, cut out as fast as possible. And I want to have some small area where I can do good. Never take that approach, okay? Myself, when I entered the graduate school, I even never thought about my becoming a professor in communications engineering. In 1994, August, I imagined to become an artificial intelligence engineer, and everybody around me stopped me. Hey, Junho, never do that. Okay, you will starve to death. Okay, do wireless communications, and I have become wireless communications engineer. One good thing is that I took almost every course in my undergraduate program. At my time, the requirement for graduation was 140 credits. And I graduated with 149 credits. So I took 3 more elective courses in electrical engineering. I never took any more, sorry about the humanities department, but other humanities courses other than required for my graduation. I filled up every credit of my requirement as an electrical engineering and math statistics department courses. Please do so. Even you do that, you will regret that I had to take courses more diversely someday. So never try to focus in your early age. You have to take a lot of courses, and whenever you take a new course, you have to have your good new tool in your box. Got it? So fill up your toolbox. Anyway, so this is covered in signal gen systems. This is covered in 전자수학 A, the mathematics for electrical and electronic engineers, or probability and random process course. And I will not much talk about this one in this course. However, this course really needs the knowledge on the random variables processes and random processes. I will just try to minimize that coverage. You have to expect that in the next semester, there will be a undergraduate digital communications course. that course really talks a lot about random variables and vectors and processes. So if you are planning to take that course in the next semester, probably you have to take, is it probably the course offered in this semester? 302? Probably not. You have to review the material so that you have better understanding and better preparation. Okay, here goes the classification of our signals. So suppose this is the set of all continuous time signals. We've just seen that this set can be divided into deterministic signals and signals with uncertainty. There are other ways to divide, is this one. Let's forget about signals with uncertainty. So let's consider the set of all deterministic continuous time signals. And then here is a very small set, less than that point I just put, but let me exaggerate the size. And in this subset, the signals have a common property. And these sets of signals are called periodic signals. So if you have an element of this subset, what kind of property, common property it has? So x of t is periodic. What does that mean? So here goes the definition. A continuous time deterministic signal, but I will drop that deterministic because I will mostly talk about deterministic signals in this course. A periodic continuous time signal, a continuous time signal is periodic if what? If what? If there exists a positive constant, of course, real number, such that x of t equals x of t plus t0 for all t. This is the definition of a periodic signal. So in order to claim that, in order to classify a signal as periodic, you have to find out some positive number that satisfies this. Got it? If you cannot find any real number, any non-negative number that satisfies this one for all t, then the signal is called non-periodic or aperiodic. Means the prefix that is equivalent to none. Okay, so this is the set of periodic signals, non-periodic signals. Got it? Now you may say that, okay, what's the good for that classification? And as you learned, and as some of you will do as your major, if you are a power systems engineer who handles generation of electrical power, transmission of electrical power, distribution of electrical power, what kind of transmission method we usually use? We use alternating current to transmit the electrical energy over the power line, right? In that case, you have what? You have your signal very good modeled as a periodic signal, like this, right? That's why in many parts of your circuits theory in the physics course or circuits course, we'll talk only about those sinusoidal signals. These signals are very, very important part of the periodic signals. But periodicity does not only mean sinusoidal periodicity. It may have some what? Square wave type periodicity or triangular wave type periodicity and every kind of periodicity. By the way, here goes another thing. Whenever you define something, see that? Here, So this is a kind of following definition. If x of t is now found to be periodic, then which means that you have provided so-called the period of the signal, right? Because in order to identify x as a periodic signal, you have to find some positive t0. That t0 is defined as a period. And now here goes the difficulty for most of Koreans and Japanese and Chinese who does not usually have those articles or the type thing. And I have intentionally put a here. Why? So the definition of periodic signal guarantees the existence of a period, right? Because you have to provide the period. So you have the existence about the notion of period. Now my question is that, is period unique for a periodic signal? Is it unique? So you have a periodic signal with period t0. Now, is there any other period for that periodic signal? And of course, any positive integer multiple of the period is also period, right? If t0 is a period, 2t0 is period. Right? So period is not a unique notion. That's why I put a period. In order to make that unique, they define so-called the fundamental period. And the fundamental period is defined this way. The smallest period of a periodic signal is called the fundamental period, if it exists. Why? Now let's consider a constant signal. X of t equals 1 for all t. Now, let me ask you a question. Is it a periodic signal? A DC, a direct current signal? Is it a periodic signal? Yes. So what is the period? Any positive real number. And is there any smallest positive real number? No. So that periodic signal does not have the fundamental period. So be careful. Of course, these extreme signals have no period, even though it's a periodic signal. But usually, okay, usually we may assume that any periodic signal of our interest have a well-defined periodic signal, except a constant signal. Got it? So any sinusoidal signal has a positive period that is smallest, and that is called the fundamental period. By the way, the inverse of the fundamental period is called the fundamental frequency. Anyway, here goes one of the most important equation in electrical engineering, the Euler's formula or the Euler's formula or Euler's identity. And it is about complex exponential, and more precisely, you may say in that way. Okay? That is the exponent rule. Here, what is E? I strongly recommend you to remember that one. I may ask you what is the fourth digit in that representation of E in your quiz. Of course, you know that that is not a rational number. That is irrational, especially a transcendental number, 초월수. But interestingly, it's very periodic. Up to is it ninth point? 2.71828, right? And we celebrate its rival. Why? I believe it's because we have March 14th, but we don't have February 71st. I really hate that, but anyway. So the E is a real number, and you know the definition. And here A and B are both defined, both are real numbers. And what is J? J or I? By the way, I prefer use the symbol J. So whenever I use j, that means the square root of -1. Okay, I rarely use I. But anyway, so it's all about the exponent rule, and you can factor this e to the a plus jb as the e to the a times e to the jb. And here, this part follows the Euler's formula or Euler's identity. And interestingly, that number is a complex number consisting of the real part and the imaginary part. And one special case is what? Is this one. So what you do is that instead of putting any theta, by the way, theta is any real number, you put pi. What happens? Then e to the j pi becomes -1. So if you move the -1, or if you add +1 on the both sides, you have this most beautiful formula in mathematics. That is not my claim. Richard Feynman, you know, the Django guy, right? He called that formula in one of his book, the most beautiful formula in mathematics. It includes 1, that is the starting point of our mathematics, right? In order to count, we have to have the notion of 1, right? And we have natural numbers, and suddenly some ancient Indians have invented the number 0, right? So it has 1 and 0, and it also has the notion of equality, but it's not a number. And also it has pi, that is 3.14 something, and it has e, that is 2.718281828. And here we have what? The square root of -1. So this is very beautiful, and also it could be used to derive almost every trigonometric identities. So you remembered 코코는 코코, something like that in your high school, right? In order to remember trigonometric identities. I still remember Samasakosa, something like that, like a magic spell. And all those, almost every trigonometric identities can be derived simply using Euler's identity. So actually, what happened last weekend is that one of my son, who is in the 2nd grade in high school, asked me, "Hey, I have a difficulty in memorizing those trigonometric identities." And I said that, okay, I will teach you using Euler's identity. And I forgot, and I have to teach him this weekend. Anyway, it may be possible to for you to see a problem saying that using Euler's identity show this blah 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 trigonometric identities. Got it? Another thing, what you learned in circuits course is so-called phasor. Okay, phasor is not pager. By the way, what is the pager? This is called BP long ago when I was at your age. At that time, we had no cell phones. Cell phones was this big, like a brick. And it was very, very expensive. And there were very long waiting line for a subscription to that service in Seoul area. So there was a very small device called pager, BP. So we put our belt and study in the library. And sometimes I feel the vibration here. And then what I do is that I could see a small LCD monitor, and there is a phone number. And what I do is that I go to the public phone, find a public telephone and make a phone call. 혹시 전화하셨어요? Something like that. Yeah. It was really the time of when Tiger was smoking. Anyway, so remember that page means that call. So at an airport, probably you've traveled through airport, and probably you see some announcements like this. 승객을 찾습니다. 조준호선님, 빨리 탑승구로 가. 이렇게 말하고 싶은데 조용하게 얘기하죠. Then what is that message? That is called that action of calling passengers or people is called paging. Okay, so paging is different from this one. This phaser is from phase. Okay, and phase is so-called 위상 or 상. And what is remembered in your brain about this phaser? The first time probably you've seen that notion of phaser was from freshman physics, where you learned alternating current. And you've seen something strange like this. Suppose we have a signal, here, A times cosine omega 0 t plus theta, and they say that it has a friend called phasor. And the phasor is what? Something like that. Okay. Is any information missing here? From here to here. Of course, there is no t. Not only there is no t, but also there is no omega 0, right? And also there is some added something, because this is a real function of time, but this is a what? Complex number. What's going on? And here goes the link between these two. Whenever we talk about the phasor of an alternating current or periodic sinusoidal signal, actually we assume that we know the radian frequency omega 0 already. Okay? And so here, in order to have this original real valued periodic sinusoidal signal back, what we have to do is that first we multiply this one with e to the j omega 0 t, and then we take the real part of this entire signal. And then you can easily show that the real part of the phasor times e to the j omega 0 t equals this real bandpass signal. So here, what is important is that real valued sinusoidal signal x of t has the phasor that represents x of t under the assumption of what? Known omega 0. Got it? So without the knowledge of omega 0, given the phasor, you cannot recover the original real periodic sinusoidal signal. But why in our circuits course, we just use the phasor of the signal? Why? Because we mostly handled so-called linear time invariant circuits, where if you apply a sinusoidal signal at a point of circuit, then every signal at any point has the same frequency. No other frequency possible if the circuit or system is linear time invariant. So we don't need the information of omega 0. We already know that every point of our circuit, as far as the circuit is linear time invariant, the signal is a sinusoidal signal, possibly having different magnitude or amplitude and different phase. So you just need the information of magnitude and phase. So it's natural to have phasor to represent the signal at a specific point. What is good for that? You don't need to handle a time function. You just need to handle a scalar. So as you remember in circuits and systems, suddenly, after you learned a lot of things about alternating current circuit, suddenly it seems that professor defined the notion of impedance and handles that complex number similar to the resistance in your Ohm's law. V equals I times R. And after the entire semester, professor says that V equals I times impedance. Why it's possible, even though it's an alternating current circuit, which handles time function? Because at every point of your linear time invariant circuit, the signals have the same radiant frequency. That was the reason. However, be careful. Given the same circuit, if you change the frequency, your impedance changes, because the impedance is a function of radiant frequency. Be careful. Anyway, I wanted to cover half of this handout, but it seems that I covered just less than 1/5. However, I believe you all fulfill the prerequisite of this course, so study very hard to be well prepared for the quiz. Even though I couldn't cover even the Fourier series and Fourier transform, your first homework will see the problems related to that. Anyway, those materials are prerequisites. Got it? So whatever happens, if the aliens does not invade, 삼체 외계인 does not invade us during the Chuseok period, we will take the first quiz that covers the entire signal gen systems. Whether this Wednesday's lecture cover the Fourier transform or not, but everything on the signal gen systems could appear on your quiz. That's all for the day.